Okay, so you hear me? Yeah, okay, perfect. So during the talk, I'm going to guide you through the work that we have been doing, which is related to the rehabilitation of language and the embodiment as such. And we'll start off by language. So if a stroke actually affects the left hemisphere, what we would typically observe is language disorders, right? So people would typically suffer language deficits, communication or production deficits. And in particular here in our lab, so 30% of the stroke survivors, 30% of stroke survivors actually would be affected by these language disorders. And in particular here, we'll be looking at a disorder that is a communication disorder that is Broca's aphasia. And this disorder is what patients present is the deficits in lexical access, phonemic disintegration, disorder of syntax, as well as reduced fluency. And here I have some examples for you to understand how is it, for example, when a patient with aphasia is asked to perform a naming task. So let's say we ask him or her to say the word that in Spanish is banco, bench.
Wow.
Did you hear it? And the correct pronunciation now, as said by a therapist, would
banco.
Be banco, right? Another example that I took from our sample is, let's say, cactus, right? That would be how a aphasic patient, severe aphasic patient pronounces it.
Cactus.
And this is the correct pronunciation. And more complex word would be aguacate.
Aguacate.
And that's the correct pronunciation. Okay, so if we go to the clinic and we want to treat those patients, I'm going to show you what are the standard ways to do it. So the standard method for treating aphasia is an individual therapist-patient therapy, where we have the patient and the therapist training language together in an individualized fashion. And what we usually train and what we usually see is repetition. So people were asked to repeat words, name words, they train spelling, syllabification, as well as articulation, right? However, if we look at the literature and if we look at the review of how this therapy is, whether it's actually effective, what we see is that there are several limitations to it. And one of it is it's normally given at insufficient dosage or frequency, as well as we see that it's the language in the context of a standard therapy is practiced in a behaviorally irrelevant context. So we're actually not training language as it's normally used in a goal-oriented way to communicate with other people, but rather we do the training of this repeating, naming, and so on and so forth, right? So what do we learn if we go into the neuroscientific basis of how the language is actually processed, or what do we know about it? Well, what we find already in 2004 or 2005, what we find is that language, traditionally believed to being a separate unit in the brain, right, is actually very much functionally coupled to the systems of motor function. So this study, this was an fMRI study which showed that when we perform, here in blue we have foot movements, so movements such as walk, green is tongue movements, and finger movements, we would have an overlap, somatotopic overlap of the areas in the motor cortex active when we actually perform those movements. So this is the plot, and when we read action words. Okay, so when I read an action word, when I read a word to wave, I would have an activity in my motor cortex, which showed that actually the language processing is not only in the traditionally believed language production areas or perception areas, but also in motor systems. What we also find is that concepts are neuroanatomically linked to sensory regions. And here I have a plot about, or a study that showed it in the context of auditory perception, but it's also similar findings are found in olfactory, in olfaction. So here what we see is that those are the area in the primary auditory cortex which are active when I am exposed to the sound of a telephone ringing, let's say. And here we say in this yellow we see an overlap in the primary auditory cortex when I'm only reading the word telephone, right? So if I'm gonna do this, I can do this experiment to you now, and can I? And I can. Oh no. And so this would be. So this is what the participants were presented with, right? The sound, and here is the fMRI scan of where we are hearing it. Here we're just simply reading the word. Another influential study was the one of Craig of 2015, when he showed that when I'm reading words and we during the time of the reading we are doing a transcranial magnetic stimulation of the adjacent areas to the ones of traditionally believed to be involved in the language processing, we see that those areas are actually very significantly involved. And it's not only the language areas, but also those of sensory cortex, motor cortex, and so on and so forth. So we see that that language is now way more multimodal than traditionally believed. And this is actually should be the grounding of a principle-based therapy, which could then aid language recovery as compared to the standard therapy. And when we look at the state-of-the-art therapies right now, we see actually that there is one therapy that is trying to combine those principles in the context of the rehabilitation of chronic Broca aphasia patients. And this therapy is done in the context of a goal-oriented language game, okay, which engages both linguistic and motor circuits. So the patients are also asked to actively perform actions and manipulate objects during the language practice. There's a component of the social interaction. So the patients, there's more than just a patient and a therapist, but patients are playing together. And there is a high intensity of training, so the dosage is quite intense, and all that is happening in the context of this card game. So three patients are sitting at the table, playing with each other, requesting and passing over objects or cards in this context. And there is a therapist that is supervising therapy and adding to it certain cues which are aiding the therapy. And actually, if we look at the comparison between this, let's say, goal-oriented therapy here represented with the black dot, as compared to the standard therapy, we see that the recovery or the changes are actually way higher when in this intensive language therapy as compared to the standard one. The standard therapy, you might also notice that pre-post training is very, very low. So that's quite a problem. Language action therapy seems then beneficial for training. However, it also presents several limitations, and one of them is that it doesn't have this full use of the multisensory cues, which we can provide using, for example, virtual reality, and it's not so accessible, right? So again, the same problem as in motor rehabilitation. Well, this therapy is only done in few centers, and it's not commonly practiced in the clinic. So here we ask a question: if we can integrate those principles into a setup, augment them with the multisensory cues, and would that be beneficial then for the recovery of language in stroke patients, right? And we did answer, or we tried to answer this question in the context of virtual reality. So we integrated those principles of language into the rehabilitation gaming system for aphasia. And here, what we have dyadic patient-patient setting. So we have two patients playing with each other. we have the arm tracking system, similar to the motor therapy, which is tracking the movements of the real hands and imposing them on the movements of the virtual hands. We have the first-person perspective, so there is the embodiment, and we added the multisensory stimuli, so we added sounds and we added visual cues to aid naming during the game. Following the suggestions from the intensive language action therapy, here also we integrated this component of goal-orientedness. So the patients were actually playing game. They were requesting, selecting and requesting objects from one another. And as well, we had the action component. So during the game, patients were presented 3 objects in the virtual reality, and they were asked to first select an object so that we can store the moment of selection of the object, and then verbally request it from the opponent. So verbally requested, saying, please give me the pumpkin, let's say. And then patient B, so the opponent, could either understand this request and pass the corresponding object, or if not, they had to ask for the clarifications. The time between the selection of the object and the reception is from the opponent. What we called it was the interaction time, and we used it as an implicit, unsupervised measure of improvement during our therapy sessions. So we tested this protocol in the context of a randomized control trial, where the control group used a standard therapy, as I presented before, in a therapist patient setting, which was matched for the intensity and the materials to the experimental group. So the patients were using those, in the context of our experimental group, they were using this 120 virtual, three-dimensional objects, and they were matched for syllable length, for frequency, and so on and so forth. And we provided several multimodal cues to those stimuli at the moment of the selection. We included stroke patients, only those who suffered chronic non-fluent aphasia, and which presented no motor or cognitive disorders that could prevent them to actually take part in the study. So our primary measure was the Boston Diagnostic Aphasia Examination, which is the classical measure for language recovery, and then secondary measures was the communication activity log, which was a questionnaire of how often would the participant, would the patient interact in the daily living, vocabulary test to measure how the vocabulary changed over time, Fugl-Meyer assessment, since we actually had a use of the arms during the therapy, and the interaction times, that is this time stored between the selection and the reception of the object stored by the system. And we made our evaluation at the baseline, at month 1, month 2, that is the end of the treatment, as well as the follow-up, that is 2 months after the end of the treatment, during which patients were not exposed to any type of therapy. So if we look at the changes at the vocabulary test, first we see the group effect. We see that the group effect, all patients together improved significantly at each time step. So both at month 1, month 2, and the follow-up. We also see that both groups, if we split them by the experimental group, that is the green one, and the control group, that is the violet one, we see that both groups improve at T1, so at month 1, at the vocabulary. Both groups improve at month 2 as well, and both of them retain the changes at the follow-up. Interestingly, however, only the control group outperforms the experimental group at T1. And you might say, why? Well, if you look at the structure of the therapy, the standard therapy, what was doing was precisely training vocabulary and naming of the words that were presented in the therapy, right? So while we were training much more communication acts, requesting, rather than the vocabulary itself. So this might be not surprising. However, if we move on to to the communication scores. So the questionnaires where we evaluated how much a patient himself and the therapist would evaluate how much a patient speaks in the daily living, then we see that only our experimental group showed significant changes both at month 1, at month 2, as well as at the follow-up. So we see that actually while the vocabulary changes might be more attributed to the practicing of naming and repetition, here we see significant communication changes that might be due to the fact of the goal-orientedness and the behavior, the relevance, the behavioral relevance of the game. Finally, if we look at the scale, the primary outcome measure, that is the Boston Diagnostic, what we see is that, again, at the group level, everyone improves, however, only from month 2, which is actually in line with the literature. And if we then look at the changes per group, we see that while both groups reach significant improvement from baseline at the end of the treatment, so at month 2, only our experimental group retains these improvements, so still shows significant changes 2 months after the end of the treatment at the follow-up, which is great news, because here we are comparing systems where 2 patients are training language in a goal-oriented way, as we use language naturally, right, together using a system that is multimodal and embodied, with only a supervision of a therapist, to individualized training of a therapist and patients in the clinic with a professional, right, therapist in the clinical context. So it's great news because we can already suppose that we can integrate these kind of systems and virtual reality-based systems into the therapy on the daily basis as a reinforcement to the standard therapy or as an add-on to the standard therapy, right, which would promote recovery. Okay, so finally, later, we wanted to understand what is the influence of these multimodal cues that we integrated to the object. So does this multisensory cueing actually aid naming in those patients? Well, this is our stimuli. So here is only the experimental group which we're taking into account that was exposed to the therapy. So our stimuli was split into stimuli that has no implicit sound, for example, house or donuts or peach, and 50% of the stimuli had an implicit sound, like a clock that ticks or a car that has the sound of the engine, right? And here, in those stimuli that had no implicit sound, we would aid them with the silent visual motor cues. Those cues are videos of lips articulating the target word. Okay, so this would be cama, here we have leche. So at the moment of the selection of the object, we would present the cue only once per trial to see whether this would aid the naming. And here, in those objects that have this semantically related sound, we introduced their representative sound. So we would have the clock for the clock, and here we go, the clock. So first, we wanted to see whether there was a decrease in the interaction time measure, that is the time between the selection and the reception of the object, in general in all stimuli, independently of whether they were provided a cue or not. And what we see is that indeed, over the therapy intervals, so this is the 40 days of the therapy, both those stimuli that were subject to visual motor cueing and those for auditory significantly decreased. Okay? But what we're actually interested in is to see what was the effect of the cue. Was there any effect of the cue? So here we split them into the cued, that is the light violet and the light bordeaux, and non-cued stimuli. that is the darker colors. So first, let's look at the visual motor cueing, so the leaves which articulated properly the name of the target word. We see that in the early trials, indeed, the difference between the interaction times between the cued and non-cued stimuli significantly differs, and here is where we quantify it. So we take the early sessions, where we see that the difference is significant, and then it plateaus at the end of the treatment. If we look at the auditory cues, so those which were provided the semantically related sound, we see a similar pattern. In the early sessions, where the exposure to the target stimuli and the cues was still low, we see the significant effect of the cue, which then later plateaus when the exposure to the stimuli was higher. So this is great news, and this shows us that indeed multisensory cueing aids word finding, naming, articulation. It's a multi-step process, and we don't know exactly what does it exactly aid, right? But the word production is facilitated when the cues are provided, especially when the target words are yet not known or infrequent. It's interesting because these cues are rarely provided. Normally, naming for patients with aphasia is aided by phonemic cueing, that is providing the first phoneme of the word, or semantic cueing, that is providing the semantic description of the meaning of the word. While those cues, which can be very easily integrated into handheld technology, let's say, are still not understood or still not studied. So this is great news. Well, together, this study showed us that grounding the aphasia rehabilitation on the scientific basis or from the principles that we know from learning or from processing of language itself actually does boost recovery and retention of linguistic function. And we can identify, in line with literature, that those principles include dosage and intensity, the use of the function, right? So use-dependent plasticity, social interaction, which has also been shown to be very significant in the context, especially of language rehabilitation, goal-oriented practice, so behavioral relevance, which then probably helps generalization of the changes into the real-world tasks, the multimodal context that was represented by the cues, as well as embodiment, so seeing myself from the first perspective and interacting in a goal-oriented way. So now the quest is to systematically study which is the contribution of those principles into the rehabilitation, right? So we know that the integrated version of the system is beneficial, but we need to understand what exactly aids what and at what stage of the recovery and at what type of stroke. And we learned last week that we can already have some hypothesis about that by making predictions from the MRIs. Now it's the quest to do that. We need to understand the role of those principles in other types of aphasia, not only the production of aphasia, but also where people are impaired in the understanding of language, and to promote the use of technology to integrate those methods and to aid those patients in the real world after hospital discharge or during hospital discharge as an add-on to the therapy. Here is the contribution of the language part, and as you might have noticed, both in the context of motor rehabilitation as well as in the context of language rehabilitation in all our system, in the rehabilitation gaming system, there is a high emphasis on the embodiment, right? So the patients are embodied, they're observing their own actions from the first person perspective, and an assumption that they actually believe that the body of this virtual avatar is theirs. So we wanted to understand, what does this embodiment actually means and what is it? How do we embody the avatar? And here I'm going to present you a set of studies with healthy participants where we wanted to understand what does underlie the ownership of a body, of a virtual avatar in this context. So what is embodiment and how can we manipulate it? So first, to define body ownership as such, we know that this is a subjective experience of having a body or feeling that a body is actually belonging to myself. And this experience, this feeling of a body as mine accounts for my experiences that everything that happens to the body is actually happening to me. And also body ownership defines, so therefore defines the boundaries of what is me and what is not me, both in terms of objects and in terms of subjects. So what is tricky about body ownership and the study of body ownership as such is that the body is always present, so we always have it with us. No, it's not like a visual stimuli that we can turn off or on, but we kind of always have it, right? So we have to find ways of how to study this, and what people came up with is the so-called virtual illusions, right? So we altered the sensation of subjects. And a very classical example of an illusion which was used to understand the principle of body ownership in this passive scenario is the rubber hand illusion. I don't know if you're familiar with that, but here we have an experimenter and a subject, and the subject has his hand placed here in what is occluded to vision, okay? And here we have a rubber hand which is placed in front of the subject, and the experimenter would stroke simultaneously the fingers of the rubber hand and of the real hand. And after, interestingly, after less than 1 minute, the subject would believe that this hand is theirs, such that if when this hand is attacked, he had the reflex of moving away, right? And so we can induce the ownership of a completely artificial object through the multisensory integration. And how do we know? Because that we made it, that the participant is actually feeling ownership over this object. So we can ask them. There are various numbers of questionnaires which evaluate this conscious perception of ownership over the rubber hand. Something more objective is this behavioral evaluation. So there is this objective assessment of proprioceptive drift. So I would, at the end of the experiment, I would ask the participant to close their eyes and to point with the left finger to their own rubber hand, where the rubber hand is substituted, and you would see pointing errors that would be biased towards the rubber hand if the illusion is present. And then we can always also use physiological measures to assess ownership, and in particular what we would be interested in is the galvanic skin responses, so how much we sweat when the rubber hand is being attacked. So if I believe that the rubber hand is mine, my physiological response will be way higher than if I do not believe that this rubber hand is mine. And the goal of all these studies, of course, was understand what are the necessary and sufficient conditions for this ownership to be present. And based on this rubber hand illusion, what we learned is that body ownership depends on the integration of spatio-temporally aligned multisensory cues which pertain to the body. So when the cues are provided in the same place or in the same time or both, then we will have higher ownership over an object that is even not not our own body. But this hypothesis would basically suggest that I can feel ownership over any type of object. So I can feel ownership over a table, I can feel ownership over a chair, which actually was not the case. So a number of subsequent experiments have proved that we cannot feel ownership over an object that doesn't have a bodily shape or is placed in an incongruent posture, right? So we need the congruency of the posture for the ownership to occur. and or an object which is outside of what we believe is the personal space. So we're coding the action space for which we're coding the movement. So what does it mean? There's not only the process, this bottom-up process of the multisensory integration, which is happening and which is driving the sense of ownership, but also this top-down modulatory process that is constantly comparing the new stimuli to be the body part and my body model, right? So if it doesn't resembling really myself, then maybe it's not me. This is all fine but if you for the rubber hand illusion, but if we have a closer look and if we compare this to all the paradigms that we have been discussing, what is lacking here very much is the action itself. So this is true when the participant is still, but we don't know what happens if in the context of self-generated movement, right? So rubber hand illusion is very much passive. So they are passively only exposing these cues provided by the experimenter, and it's completely isolated from this self-generated goal-oriented movement, right? So it explains the story, but it doesn't explain the whole story. And the principles of ownership in the context of self-generated action, which we want to control, or which we want to manipulate, or which we want to rehabilitate, remain unexplained. So first we wanted to bridge this gap and understand how is ownership when we actually move in a goal-oriented manner. So to know this, first we wanted to understand if it's functionally coupled to the motor system. Is ownership coupled to the motor system? And we tested it in a virtual reality-based study where we had a virtual rubber hand illusion. People were viewing the scenario through a 3D headset, and they were exposed to this visual-tactile integration, visual-tactile stroking. So they would see and feel their fingers being stroked. In the one hand it was the real hand, and in the other one the virtual hand that they were seeing through the head-mounted display. So we had three conditions. Okay, here the important thing that I need to mention is that to see whether ownership has an effect on action itself, what we ask them to do is to provide a motor response in the form of a click, always when their index finger is being stroked. Okay, so all the participants underwent a baseline condition to evaluate the default reaction times, and then they were split into three conditions. The first one was the congruent one, where they felt and they saw the finger being stroked in the same time and in the same place, and they were asked to give a motor response when the index finger was stroked. This was the incongruent visual condition, when the stroking was incongruent, so I would feel a different finger being stroked when I see, and I'm asked to give a motor response when I see that my index finger is being stroked. While in the last one, exactly the same as in the previous one, the stroking is incongruent, but I'm asked to deliver the response when I feel that the index finger is being stroked. And after the end of this experiment, we would introduce the threatening event, so to measure the spontaneous reactions, so the galvanic skin response to this threatening event. And we expected that in the congruent condition, when the visual tactile stimulation is spatio-temporally aligned, we would have higher ownership, while here in those two conditions, the incongruent visual and incongruent haptic, we would have lower ownership. Well, first we looked at the questionnaires. So the control questions were not affected as expected. And then when we compare the self-report, we see that, as expected, in the congruent condition, participants would report higher ownership than in both visual and haptic conditions, so in both incongruent ones. This was supported by the results from the galvanic skin response. So here at the time 0, we are introducing the knife, which is stabbing the virtual hand, and we see that the blue, so the congruent condition, is significantly higher than both the incongruent visual and incongruent haptic condition. So this is very much in line with the literature. And then we wanted to understand what is the motor response. So how is the motor behavior affected? So here is the incongruent haptic condition, incongruent visual condition, and congruent condition. Blue is early trials, black is middle trials, and red is late trials. So we see that in all of them, the reaction times decrease over time. However, as you can see, in the congruent condition, independently of whether it's a late, middle, or early trial, they are significantly faster, the responses, than both in the incongruent visual and in the incongruent haptic. But this is all fine, only if we see that there is a relation really between the ownership, the perception of ownership, and those motor responses. So we run a correlation to evaluate that. And first we wanted to understand what is the relationship between the subjective measure of ownership with these motor responses, and then we wanted to understand what is the relationship between the objective measure of ownership, that is the galvanic skin responses, with the motor responses. And we see that in both cases we have a highly significant correlation between the two, which suggests that that motor performance here operationalized in terms of reaction times is highly correlated with the subjective and objective experience of ownership. And this is great news. But now we want to understand maybe what is the mechanism, right? So is it possible that body ownership is actually coupled to the motor system, and in which sense? So we asked the question whether body ownership depends on the similar mechanism as motor control. And if, just to remind you, for the learning or motor learning to occur, Belen said more about this, but I'm going to just briefly recap. What we need is, first we need a goal-oriented task, like an air hockey, for example, and we need to have a goal, right? And then, apart from the goal, we also need action-driven sensory feedback, right? So we need the visual feedback of my motor behavior, as well as auditory feedback, any type of modality, right? But I need to have a feedback from it to learn the errors that I'm exposed to. I'm going to probably learn faster, learn slower, but I need to have an evaluation of my errors. So this is the components that I need. And we also note from literature that the congruency of all the task-relevant feedback is critical for performance, right? So my system is plastic and adaptive, and if I start manipulating, as Belen has shown, if I start manipulating and tricking your brain, introducing errors, you're going to be adapting to them, right? So we assume that if ownership depends on the same mechanisms as the motor learning, then it would be affected similarly as motor control when we start introducing sensory errors, right? And we decided to test this hypothesis. We tested this in a virtual reality-based task. There was an air hockey task when we had people wearing the head-mounted display. They visualized this air hockey field, and their task was to score the goals by hitting a puck into the goal. They were exposed to a training where all the auditory cues were congruent in both conditions, and then in the experimental group they were split into two conditions. One where the auditory cues were congruent and expected, so as we can expect, and once when they were incongruent, and the incongruencies were different. Sometimes they would be coming either the sound would be anticipated or delayed, or they would be spatially incongruent. So instead of having a sound on the left, it would be happening on the right, and so on and so forth. So here we expected that, of course, like as you might predict, that motor performance is going to be clearly affected if I'm introducing errors, right? But let's have a look at what happened, right? So this is the scores. This is our results first from the scores. So we look at what is the total normalized success per condition, and we see, okay, indeed, in the incongruent condition, the black one, the scores were significantly lower. And then we looked at the directional error. So we looked at the difference between my initial vector and the correct one leading the pack directly to the goal, right? And we see that while in the congruent condition, the median error would be decreasing over trials, in the incongruent condition, it's actually starting to increase, right? Then if we quantify this difference, so we quantify the total error, this difference is actually significant. But this is fine for motor, and this is something that we can be expecting. What about the ownership? Did this manipulation affect ownership? So when we look at what the participants reported, what did they say in our questionnaire? We say, indeed, when the auditory feedback of my goal-oriented action was unexpected and incongruent, my perception of ownership over this avatar was significantly lower than when all the stimuli was congruent. And this was supported by the objective measure of ownership, that is the galvanic skin response after threatening the virtual hand. So again, here is the moment of the presentation of the knife, and the blue one is our congruent condition where we see high increase after threatening the hand, and here is the incongruent condition where the increase is lower. Obviously, in both conditions, we always expect certain level of increase because we're exposed to the knife, but the difference between the two is significant. So not only on the subjective but also on the objective measurement, we see that ownership in the context of action is actually affected by cues that are self-generated and pertain to the task. This is a novel finding, which further suggests that it might be that ownership is then about control as much as the motor function is, right? So we wanted to understand, is this the case? Is ownership about controllability? Well, I'm sure that some of you have played, maybe not Mario, maybe someone Mario, but you guys played computer games. And I can also, I'm going to take the challenge of predicting that if you end the game, you would rather shout, I won the game, and not Mario Bros won the game, right? If you think about it, it can have some interesting implications for the sense of ownership over these avatars that we're controlling, independently of whether it's a computer screen or if it's a virtual reality, right? So what does this actually mean? Does it mean that we owe Mario? Well, let's see. We wanted to understand this, and we did test it, again in the context of a virtual reality-based study, where people were presented this green forest or a garden, and they were controlling. So in order to induce ownership over your avatar, the effector was a virtual log. So it was a piece of wood which had to be directed to the goals. Those were these virtual fountains. And at the end of the experiment, to understand whether there was an ownership induced over the log, what we did was we threatened the log. And so how could we manipulate these log? Where we designed the mapping between the hand movements of the participants and the virtual log. So you were using a controller, and if you move the controller from the center to the right, you would move the log, let's say, forward, then to the left, it would be backwards, and so on and so forth. And we presented the participants to a training block where they were to actually acquire the mapping between the virtual effector and their body, and then we split them into a congruent and incongruent condition. So congruent condition, you might imagine it was fun because you were having your tool and you were directing the log into the fountains, right? Incongruent condition was a bit more tiring. So here we had the random mapping between my effector and my body movements, right? So here you can imagine a slight frustration. Yeah, so then both groups had to perform this experiment for the time of 15 minutes, and then we introduced a threatening event. So we attacked the knife, and then we debriefed them. So here this is an example of the log. So here you can imagine that there is a participant who is moving their hand with the effectors and is controlling the movements of the log accordingly. And this is the scene of the attack. Okay, so did they feel ownership over the log? Here is the control enough to induce ownership. The self-report study showed that significant difference between the groups. So they did report ownership over the log, right? This plot is interesting because if you compare the classical scores of ownership in the rubber hand illusion, or also in our cases, in case of when you're moving an avatar, this score is normally higher, right? So we are not expecting, I guess, participants to feel as much ownership as over your own body, but you see that the control, and maybe with time the exposure to predictable movements of an effector that is not bodily and not within your personal space, so-called, induces a level of ownership over it, right? And interestingly, then it's also further supported by the log, so by the threatening event. So if you look at the amplitude of the GSR signal post-threatening event between the conditions, we see a significant difference between the groups, which further supports the idea that it might be the control that is inducing ownership. So further supporting the hypothesis that in the context of action, motor function and ownership as such are coupled, possibly functionally coupled. Finally, we wanted to understand what is the contribution of everything that is outside of the action, right? So now we have been talking about me, action-related, action-dependent sensory feedback, and effectors, right? So everything was about control. What about all the rest? Like, we're acting within an environment which we're also modeling constantly, and does it have any effect on the way we perceive our own bodies? So here we use the same setup as in the previous experiments, but what we did was we manipulated the congruency of the environment, not of the action outcomes, right? So in the training, both the environment and all the cues that were action dependent were congruent, but in the experimental block, in the incongruent condition, you would see manipulations of different parts of the scene. So the clock would start moving in an unpredictable way, the benches would start shifting in an unpredictable way, and so on and so forth. I'm going to show you now in this video. And then again, at the end of the experiment, we threatened the virtual avatar to measure their autonomous responses. So here is a congruent condition where everything is congruent. So, and here will be the incongruent condition. So this is what was happening. So basically, the virtual saural time. So the virtual saural time was altered. You saw that the daytime was changing, and the background sound was indicating the location where we are was changing. There was a concert. There was a hockey pitch, and so on and so forth. the velocity in the direction of the hands of this clock that was in front of you was changing, and the bench is rotated now. And so, but crucially, in both conditions, all the action-driven cues, so all the sounds and all the visual and auditory feedback that was resulting from the action was congruent. So first we wanted to understand what happened with performance, and we see that so here we have the angular error, okay? Green is the congruent condition, the black is the incongruent condition, and we see that over the training where both conditions, in both groups decreased, so they improved significantly the performance. And then you see that in the training, in the experimental condition where we introduced the manipulation, independently of whether the environment was predictable or not, the error plateaued. And if you quantify it, we see no significant difference between the two. However, if you look at the ownership scores, so when we quantify the conscious experience of ownership when the environment does not match my prediction, we see that actually the ownership is significantly higher when I can predict my environment, and my self-report is decreasing if the environment is incongruent. Similar does the GSR, and if we look at the number of the responses of the GSR, we see that in the congruent condition we are way more affected by the threatening of the hand than we are if the environment is unpredictable, suggesting that it might be that if I don't believe the environment, I don't believe me either, right? We wanted to further support this finding, and to do so, we calculated this hand withdrawal, right? So you know that when you are attacked or when you are threatened, you have this withdrawal effect. So in this case, for example, you were expecting that the hand is going to be moving faster, right? So we quantified this, and here is the response, like the hand withdrawal effect after the threatening. And what we did was, this signal is quite noisy, but what we did was we calculated the difference, the cumulative difference over time between the velocity in the two conditions, and we see that it reaches significance at second 4. So we see that at second 4, the behavioral response, which we could call the withdrawal response, was different, and then it came back to normal. So this suggests that not only the task relevant action cues are building our sense of self, but also the environment and the cues from the environment are relevant for how we perceive ourselves. And so general discussion of the second part of the talk, that is related to the embodiment, where we can say that body ownership depends on both action-driven cues and those that pertain to the environment. And if we now look back at this model that I presented, or the theory that I presented you before, that was coming from the rubber hand illusion, which was telling us that the necessary conditions for body ownership is the integration of multisensory cues, spatial-temporally aligned, and the congruency of the novel stimuli with my body schema. We can now complement these findings, and we can say that it's integration of not only the spatial-temporally aligned cues which pertain to the body, but also those that pertain to the action, and also those that pertain to the environment. And we don't, therefore, not only need the congruency of the novel stimuli, which is related to the body, but also this one that is the action-driven sensory signals and the behavior of the environment. So we're constantly predicting not only self-related signals, self-generated or received, but also those that are around us, right? And all these signals seem to build our sense of self and increase the embodiment or decrease the embodiment, if you wish. So now the future work will definitely include understanding how we can then use this principle of embodiment in the therapy of motor function and language function in order to increase the belief, right, that the patients are actually embodying the virtual avatar, and to increase the belief that those errors that we are manipulating are actually our errors, right? And like this, we believe that we can increment the recovery of both motor and language functions in this case. Thank you.